14th session of IMSC 60 celebration. So we have 4 talks in this session. So our first talk will be given by Professor Mythily Ramaswamy. So she is an adjunct faculty of CMI, before which she was in ICTS Bangalore. So today she is going to talk about the differential equations, a glimpse. So she is a fellow of the Indian National Academy and the Bangalore Academy also. She has several other accolades. So without much ado, let me request the speaker to start.
Thank you for your kind introduction, and let me thank the organizers for inviting me to talk here. It's a great pleasure to participate in this 60th anniversary, 60th birthday of the Institute of Mathematical Sciences. My connections with IMSC grew when my ex-colleague, former colleague, Professor Kesavan joined here, and also briefly Shrikant. So that time I used to come very often, and I knew all this setup. And once they retired, and we also had a common student, TV Anoop, and so it was very regular visits to IMSC. After that, it is reduced a little bit, and I'm very happy to renew it now with all the younger, enthusiastic colleagues here. And I wish you all great success and further growth for this institute. So so how did this go up? No, sorry, I'm going in the wrong direction. Reverse. I did that. It's going forward. You finished the whole talk. So you know now. Anyway. Yeah, I don't know how it goes only one direction, so I can't control it very well. Maybe that will work. That's also not working. Okay. Let me come back to the first. Here, this may work. Page up, page down, right? This one? No, this works. Arrow works. Okay, thank you. So but maybe the pointer will work, I hope. Yeah, I'm currently in CMI, but I'm also attached to ICTS, where I have this Nazi Senior Scientist Fellowship. So I'm in both the institute. Now currently for teaching, I'm attached to CMI. Okay, so it's very difficult to be the speaker at the last session, blocking you from your dinner. So excuse me, I have made it as light as possible. So either you may be bored and say that it is too elementary, but it's better than having all the glorious details and boring you with my hard theorems. So it's going to be very light talk. Only towards the end I try to tell you a little bit about the work done by our group. So let me start. The outline is this. I start with a brief preamble about differential equations. So far nobody talked about PDE, I think. So I want to take an analyst viewpoint, because you have already heard a lot of differential equations in the physicists' talks. So this could be very different from what they were discussing. Then the models, what our group is looking at is fluid models. So I want to briefly touch upon. And then the other thing what we are trying to do is the control questions, which I'll just touch upon, not going into details. So I'm going in the wrong direction. Yeah. So we all know that modeling a natural process, physical phenomenon like melting of ice, radioactive decay, and for some of them, spring motion or heat conduction, many of them often leads to differential equation. That's how we are introduced in a differential equations course. Now we formulate it as a mathematical model. We also heard a lot of other models in the in the talks during the earlier days. So we can either use approximations or assumptions based on experiments or observations or physical laws. And our aim is to solve them somehow, solve them analytically. If you get an explicit solution, that's all the better. If not, at least you solve it numerically or approximately. So that's the aim. Now then you come back and interpret your mathematical results in the context of the phenomenon and try to understand the phenomenon. Hopefully we can make predictions and we can control it by using various parameters like the spread of the disease. As probably Gautam Menon talked in the morning, I missed the talk, but about how a disease spreads and how do we control. These are very important questions. So how do you build a mathematical model? So you know that if the object of study is either in the equilibrium state, if it is in the equilibrium state, then balance of various forces will give you the equation. Or if the object is varying with time and then you model it using the rate of change d by dt, and that gives you the differential equation. So the prime example is Newton's laws of motion, and which help us to understand the motion of bodies, celestial and terrestrial. So I would say the father of applied maths and differential equation is Newton. So let us see, he started it in 1643, he was between 1643 to 1727. And it was during this time, the famous story goes, the apple fell on his when he was sleeping and he wanted to know how they move. And even today in modeling, most of the time that F equal to ma is a common law that we apply to derive the mathematical model. And we also integrated them. He introduced the integral calculus. He also told us how to solve the differential equation. They were ordinary differential equations. Very soon it was realized that the variable, space variable could be sitting in a plane or in the whole space. So it led to partial differential equations. And there were many conduction of heat and diffusion of chemical, all these led to heat equation, which is of parabolic type, and vibration of a string. Actually, the first one to start with was D'Alembert, and he started asking this question: if I hold a string and if I pluck it, how long will it go on vibrating? So that was the wave equation. He posed the question and he also solved it, and we all studied today D'Alembert's method for solving the wave equation. And then there are higher order wave equations also, that vibration of a membrane, vibration of a beam, all these came up as they were all hyperbolic type. And potential flow, Laplace started this. I haven't written these the years. They are all in the 18th century, and that is how all these were famous important linear equations. And the initial trend was they were able to write down the explicit solution, and the way they could understand how it behaves and how it explains the phenomenon. And let me look at nonlinear equations. That's also very important. Iconal equation or equation of geometric optics. This was Hamilton. In his study of light, he wanted to prove the light propagates along a straight line. So he introduced this iconal equation, and now it is called iconal. And he even explained to us how to solve. And there are also other equations from geometry, minimal surface equation, Monge-Ampere equation. There are many. So I just stop there. Then fluid models, the famous fluid models, Euler started one model, and Navier-Stokes is the most popular model, which compressible model as well as incompressible model. And Korteweg-de Vries model and Benjamin Bona. There are many fluid models today. They have very important applications in atmospheric sciences. Today, the weather prediction, we are using Navier-Stokes equation, and oceanic sciences, aeronautics, and blood flow, lot of biology problems, or the airflow in the lungs. So these are all modeled by these equations. So we want to know how to solve them, how the solution will look like. So let me take a minute to look at Claude Louis Navier. He was a French engineer. What in 18th century he wrote down this equation, and later along with Sir George Stokes, a British scientist. So of course probably they never met, but they had this, I don't know, the equations finally came out to be known as Navier-Stokes equation. Today it's one of the important areas of research in this. Just as an embarrassment, Claude Louis Navier was an engineer, and the bridge he built over the river Seine unfortunately collapsed. So that was a bit of an embarrassment, but nevertheless his equation is holding strong even now. So the PDE arises in several areas. The physics, the connection, the symbiotic relation between physics and mathematics, physics and PDEs is well known. And in fact, somebody mentioned in one of the talks, Wigner, the scientist, the physicist, mentioned the unreasonable effectiveness of mathematics, because many physical phenomena could be explained using mathematics. I see Wigner's statement on the wall just outside, so I remembered that. And in those days, as we saw in the 17th, 18th, 19th centuries, there was no clear boundary between physics and mathematics. D'Alembert and Euler, Poisson and Laplace, they all came, studied both, and could apply one to the other. And how about the other aspects of mathematics? The other areas of mathematics also had connections with PDE. And Riemann was the first one. He used the PDE to solve many problems in complex analysis. His way of attacking complex analysis was through differential equations, as we know, Cauchy-Riemann equation, for example, and he used it in several other contexts. And and Dirichlet principle was another, he pioneered to use that Dirichlet principle. And in topology and symplectic geometry, there are many equations, Laplace-Beltrami and Dirac operator, Young-Mills and Seeberg-Witten, and also the algebraic geometry and integrable systems seem to be connected. And also in the, what surprises me is the automorphic forms in number theory. That's what I learned from Kleinerman's review, which was very interesting. He gives the connection with other branches also. So he says the spectral theory of Laplace-Beltrami operators and scattering theory of wave equations seem to be connected with in number theory. So you could be coming from physics or any branch of mathematics, so your viewpoint is going to be surely different. So you could be an applied mathematician, then you are interested in the underlying phenomena and not the PDE as such. Or you could be a physicist or a geometer or analyst like us. The viewpoints and the questions we ask are all very different. So I am going to look at it from the analytical viewpoint. For us, existence of a solution and uniqueness of a solution is very important. So it is not necessary I should write down the solution, but I should have an idea about the qualitative properties, or whether there are many solutions, whether they break down, or they have, how singular they are, how regular these are some of the questions. So it was Hadamard in the 19th century who introduced this well-postness concept, which is what we are using even today. So naturally one would think it's enough to have a solution which is unique, but it's not unique, that is not enough. He pointed out the solution has to be continuous with respect to data. What it means is, A small change in the data should lead to a corresponding small change in the solution. There cannot be a drastic change. So then he called it a well-posed problem. And then he showed for elliptic, parabolic and hyperbolic problem, what are the side conditions, initial boundary, what should be the right side conditions to prescribe so that the problem together with the side condition will be well-posed. So that is what we are still following. And he also classified the solution, the second order PDEs into elliptic, parabolic and hyperbolic. It's interesting that Hadamard himself migrated to PDE. He started somewhere else. He started with matrices, determinants. There is a Hadamard matrix which is well known, and Hadamard's inequality for determinants are also well known. And then he moved to complex analysis, and then he took up the chair of astronomy and physics, and then he started moving into mathematical physics and PDEs. And he had fundamental contributions here. He also introduced how to use a method of descent to solve the wave equation. So for the three important linear equations which I mentioned, Laplace, wave and heat, we know the well-developed, we have a well-developed existence and uniqueness theory. We know when the problem is well posed. But when you come to nonlinear equation, it's going to be many questions remain. But first of all, we have to clarify what we mean by solution, because the natural thing is you would expect a classical solution, a function having as many derivatives as required in the differential equation, and it should satisfy the equation pointwise everywhere in the domain. This is the natural definition we would expect. But it doesn't work all the time because it's too restrictive. It may not exist and it will break down. So that is why very soon it was realized that you have to abandon the search for classical solutions and ideally look for a generalized solution. Then how to generalize? That is also it's a big question. So a generalized solution, in contrast, it satisfies the PDE not necessarily the pointwise sense, but in an integral sense. That means you multiply the PDE by a suitable test function, ideally a function infinitely differentiable and with compact support, and integrate it over the domain where you are working. So in that integral sense, we want the differential equation to be satisfied. So that is what is justified by theory of distributions introduced by Laurent Schwartz, that provides a satisfactory framework to search for generalized solutions. Today, most of the nonlinear equation, we start with generalized solutions. And the popular method is you first solve the equation in the generalized, for a generalized solution. Then you go back and examine the regularity, how smooth it is. Is it continuous? It's differentiable. And then you come back and you answer. It could be even a classical solution. So this is one of the popular methods. Now, but why do we want to look for a generalized solution? There are many reasons. One is that, as I mentioned, D'Alembert was the one who gave a formula for wave equation, solution of the wave equation, and it caused a lot of uproar in the mathematical community at that time, because the formula seemed to make sense even for discontinuous functions, which sort of put off many of the classical mathematicians at that time, because they couldn't accept a PDE to have discontinuous solutions. But later it was realized the waves breaking in the seashore, the wave comes all the way to the seashore and then suddenly breaks. There is a discontinuity clearly seen in practice. And also in explosions, we do hear the sound wave, shock wave. So they have to be explained. It may not be possible to explain them in the classical setup. So can you explain it through such solutions? And in scalar conservation laws, even if everything is smooth, The equation has smooth coefficients, initial conditions are smooth, but you do get shocks. So they are inherent in the equation, so we need a solution framework to explain all this. And also in the elliptic equation, it was shown, of course, I said Riemann anticipated this through Dirichlet principle. In the case of elliptic equations, by looking for solutions in Sobolev spaces, which are equivalent of the classical C1, C2 spaces, but in the Lebesgue setup, the LP setup. So the existence and uniqueness theory is a lot more simplified because I could use very powerful tools from functional analysis and operator theory, and then we could separate the regularity question and then examine this. So similarly, viscosity solution, which was introduced by Pierre-Louis Lyons recently, and that makes it easier to handle even degenerate elliptic equations, and that is very important for passage to limits. The classical solutions will not allow you to pass to the limit, whereas this will allow us. But the problem is, the price to pay is the inconvenience of too many generalized solutions. We are in a way, we are opening the floodgates. There will be too many generalized solutions. You have to pick a correct one. So it's very important to pick the correct, physically relevant by suitable additional conditions. So I'm not going into this. So let's give a quick example of a Dirichlet problem. For example, I want to solve Laplacian of u. Laplacian is the sum of second partial derivatives of u equal to f in omega. U is 0 on the boundary of omega. I want to solve it in a weak formulation. So what do? You multiply by phi, which is a smooth test function. So d omega means C infinity functions with compact support, and then the Laplacian, when I integrate by parts, it will become gradient of u dot gradient of v, and there will be no boundary terms because my function vanishes on the boundary. So this could be taken as the weak formulation. This is what I said, you can integrate with the test function and interpret, instead of the PDE pointwise, I only demand this integral inequality be satisfied. So this will make sense. It's enough u is in L2 and gradient of u is modulus of gradient of u is in L2 and f is in L2. This will make sense. So it's a very, very weak setup, and I can work in this getting the existence of a solution. And so this is a weak formulation. So these are the Sobolev spaces. That means the weak derivative is also in L2. That is the H1. So I look for H1 0, the function vanishing on the boundary. As an example, the advantage is I could use powerful Hilbert space methods because I have a bilinear form, and whether it can be solved. That can be answered using functional analytic techniques. Okay, so let us go on. But this I gave the example because this can be used for Navier-Stokes also, the incompressible. So let me go to inhomogeneous incompressible fluid description. A description of the incompressible fluid with divergence free velocity. This I am not deriving, but even again Newton's second law, you can use F is equal to m into A could help you. Conservation of momentum will help us to write down this equation. So the velocity vector, I am writing it in R3 because R3 is the important dimension we live in and we want to understand. Velocity is now a 3 vector, u1, u2, u3, and the pressure is a scalar of the fluid, and they satisfy this equation, the time derivative of the velocity vector, and this has to be interpreted u dot del. Del is the operator, d by dx1, d by dx2, d by dx3. So you take the dot product and multiply by the vector u and gradient of p. As you see, it's a vector equation. So it has 3 components. So there are 3 equations in the first one, and divergence of u is 0 is the sum of all the first derivative is 0. That is du by dx1 plus du by dx2 2 plus d by dx, so that will also be 0. And viscosity coefficient nu is supposed to be positive. So this is non-linear because it's like a quadratic non-linearity. So what can we say about the existence and uniqueness, because it doesn't fall in the previous setup. So it was Jean Leray, who used a compactness method to produce a global weak solution. So he produced, that's why I introduced the weak solution. He proved a global weak solution. Global means for all time. This weak solution exists, he proved. But the problem is we are not able to show the uniqueness of the solution in 3 dimension. In R2 we are okay, but R3 is the important dimension where we don't know the answer. Or if you restrict your data to be very small, or you restrict your time interval to be very small, then you know there exists a smooth solution. So that is known, but it is not known whether these smooth solutions extend for all time smoothly, or do they blow up? Is there a blow up of the velocity or pressure, or what happens? That is also not known. Now this has led to the famous Millennium Problem Prize by Clay Mathematics Institute. So the problem is to decide if there exists a smooth global solution for reasonable initial conditions, or if there exist certain initial conditions for which the solution blows up. We still don't know, but we live with what we have. So what we could do is, so the aeroplanes are flying, engineers continue to work with Navier-Stokes, and mathematicians continue to work with Navier-Stokes model. And even we study fluids plus structure interaction, that is a body moving in a fluid. That is also we are studying with enough assumptions and restrictions. Okay, so let me touch upon quickly the control of differential equation. There are many questions we can ask about the control of differential equation. That is, fluid control is a very important practical problem. So can we control the trajectories of the differential equation to reach a desired target? And we can control it in an optimal manner. These are all practical problems, and more important is, can we, if the system is not stable to start with, can we use a control to stabilize if it is unstable? So I'll briefly indicate, if there is time, for how much time do I have? 5 minutes? Okay. So I'll briefly indicate what the stability concept, how do we extend it to PDE. Some of these techniques have been extended suitably for linear PDEs and some non-linear PDEs like Navier-Stokes also. So let me start with ordinary differential equations, because that involves only a matrix. We can understand it more easily. Solutions of a system of differential equation in Rn. So this is Zt is a vector in n vector sitting in the Euclidean space Rn. And z prime t I denote dz by dt. So the time derivative is, the dynamics is given by A times zt. What is A? A is a n by n matrix. So the 0 is the equilibrium point, which means if you start at 0, you don't move, you just stay there. So if you start near 0, will I come back to 0 or will I blow off to infinity is the question. Now we know that it will tend to 0 exponentially as t tends to infinity, provided all the eigenvalues of A, sigma A I denote the spectrum of A, real part of the eigenvalues of A all are negative. So if it has all the eigenvalues on the left half plane of the complex plane, then we are safe. The trajectories will go towards 0 or the system will be stable. Suppose not, then A has some, let's say A has some eigenvalues which is sitting on the positive half plane, then some trajectories could blow up. So the idea is to use a control term to bring the trajectories 0. The control will change the dynamics, of course, but how to use it? Because the A is at t plus I am going to use the control B. The control is given to you because you may know, like in the car, you may know how to use the accelerator or a brake, which are all the control in your motion. So the control is given to us, but what is not given is the control vector ut. So if I would like to start with this azt plus but, b is given, a is given, and find the control vector u. So to be determined. So now we know in the ODE setup, it has been used very often. We can find a control U steering the solution to 0, and we can even find it in the feedback form. What it means is the control at every point depends on the state of the system ZT, which is what is natural. It should read the state and then control. So this has been done in the ODE setup, and if the eigenvalues of A plus BK, they all lie on the left half plane and the complex plane, then it will be stable. So by adding this BK, we would have stabilized the system. Now the question is, how do you do it for the PDE? So I'll just quickly indicate what do you do for PDE stabilization and then stop. So to extend these techniques to PDE, the main idea is to view the PDE as an ODE, ordinary differential equation, but evolving in an infinite dimensional space. So let us start with the heat equation, that is dy by dt minus Laplacian of y is f. It's satisfied in some omega cross 0t, and you supplement it with some initial condition and some initial condition y naught x and some boundary condition satisfied, let's say 0 on the boundary for all time. Now I want to know how to view it as an ODE. So let us go to this. We are going to rewrite it as an operator equation. Du by dt equal to aut, u0 is u0, but this a is no more a matrix evolving in Rn or n by n matrix, but this a is going to be an unbounded operator which will involve d square by dx square, the differential equation. So naturally it will not be defined in the entire space, it will only be defined in the domain dA, which are twice differentiable in this case. So only then I can take the second derivative, right? So dA in a suitable Hilbert space of function, and then we can show that it will generate a C0 semigroup ST on Z. Then I can write the UT in terms of the semigroup formalism. So the semigroup theory will tell me that given every U0, there is a unique solution. So I will be able to get the representation. And then we can also do the spectral analysis of A, and that will help us to construct a feedback control operator to stabilize the equation. All this has been done over the past few decades, so I am just finishing it in one line. But the idea, this is for linear equation, because you see the heat equation was a linear equation. Next question is, how do I extend it to the nonlinear equation, which is Navier-Stokes? It can also be done, but only locally, because what you do is you can set up an iteration through every linear operator. Each iterate will solve a linear equation, and then if you can converge, you would be able to find the feedback control. So maybe this is what our group is doing, so I don't go into deep theorems here. Let me stop here. The Benzusan-Prato-Delfort meter is the infinite dimensional control, infinite dimensional system where the PDE control is explained. And most of what I gave in the beginning is taken from Kleinerman's review article in Geometric and Functional Analysis, PDE as a unified subject. He says PDE is not a unified subject, but collection of lot of islands of knowledge. And Brezis and Browder have written PDE in the 20th century, that's a review article. And I had written one review article in which I explained the control questions. So I stop here. Thank you for your patience. Yeah.
Okay. Yeah. Thank you, Professor Mythily.